Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about collaborative filtering, which is a very important task in recommender systems, where essentially you try to aggregate data from many users and many products. That could be, for example, movies, but they can also be just, books or household products that people are interested in, for example, in Amazon. You try to aggregate all of this data to predict the preferences of users that have not yet purchased a certain product or not yet watched a certain movie. And what we're going to do is we're going to show you that this can be framed as a matrix completion problem, where you have a matrix which has some missing entries, and that you can actually solve this problem and obtain a model to perform collaborative filtering using low-rank models. And these are actually pretty effective models in practice that were developed originally to solve the Netflix challenge, along with different other techniques, but they were very prominent. The Netflix challenge happened already, I'm going to say maybe I'm wrong, but like 10 years ago, perhaps, or a bit more, where Netflix offered $1 million to different teams that were trying to improve their recommender system algorithm. Okay, let's get to it. So we're going to talk about matrix completion for collaborative filtering. And the idea here is that, these are the goals. The goals are, sometimes I forget the order of my slides. The goals are, we're going to explain how to perform collaborative filtering using low-rank models. We have a previous video on low-rank models, so you might want to take a look at that if you don't know what these models are. We're going to show how to fit these models to data, and we're going to apply them to predict movie ratings, both in a cartoon example and also on real data. Okay, so the motivation of using low-rank models in general is that we often have data where each data point is associated to two entities, and that definitely happens in recommender systems, where we have ratings given by users to different users to different products, for example, movies. But this also arises in computational genomics, where you could have many cells, each of which can be associated with many genes. So if you look at expression level of each gene in each cell, then low-rank models become quite useful to model this type of data. And in the low-rank model video, we have an example where we show how to analyze temperature data, where we have temperatures at different locations and different times. This kind of data, where each data point is associated with two different entities, can be expressed as a matrix, where we put the data inside the matrix, and the column indicates one of the entities, in this case a user called Mary, and the row indicates the other entity, in this case a movie called The Dark Knight. So Mary decided to give a rating of 5 to The Dark Knight. These are ratings from 1 to 5, so Mary really liked The Dark Knight. And now in collaborative filtering, recommender systems, what we want to do is we want to figure out what these values could be. These are missing ratings because these users didn't watch those movies. This is a matrix completion problem because we have a matrix and we would want to complete it. We would want to impute those values that are missing. The first time you see this problem, you should be like, this seems impossible, no? Like, I have a matrix, there's some missing entries, you could write in whatever you want there, right? Like you could write an 8, you could write a 23, you could write a -5. So this seems like an ill-posed problem, unless there are more assumptions. And the assumption we're going to make is that the users, their tastes are actually quite related, and the movies or the products in general are also kind of related, and we can explain the ratings as a low-rank model where there's R factors. And this perhaps easier to explain for a rank 1 model, which is how we did it in the low-rank model video. Maybe let me pick here. No, this is in a couple of slides. I should have made a slide with just a rank 1 model, but bear with me. So basically here the idea is that each of these factors within the rank R model, okay, basically express, let's start with, let's say that these are the users. So we have a certain pattern of ratings that groups the movies. So maybe here, this will have very large values for superhero movies and very low values here for romantic comedies. And this is the example we gave in the low rank model video. And then conversely here, it will have high coefficients for movies that like superhero movies and don't like romantic comedies, and low values, for example, maybe here, for users that don't like superhero movies but like romantic comedies. Okay, but that's only one factor that might not, that might be complemented by other factors. So that's why in the low rank model we have these additional columns, each associated with an additional row, which are basically different common patterns that are found within users and within ratings. And the way we combine them is we multiply them with each other, okay, coefficients corresponding to the movie and to the user. We combine them to approximate the rating. The important thing to notice is that this guy has a number of entries that is equal to the number of users times the number of movies. Okay, I apologize for my handwriting. Whereas here on the right, and I'm going to erase so that it's kind of clearer, here on the right, the number of parameters is actually quite a bit lower. If we have R, and R is usually a small number, as we will see in our real data example, we have R times the number of movies plus, and this is very important, it's plus R times the number of users. Okay, so it's basically R number of movies plus the number of users. Okay, so imagine that you have hundreds of users. Let's say 100 movies, 100 users. This would be 200 times the rank, whereas this would be 100 times 100, 10,000. Okay, so the low rank model really reduces the number of parameters used to represent the ratings. Why is this important? Because now imagine that you have some missing entries. If you manage to fit a rank R model, you might be able to pull this off, because remember, I have just shown you that roughly speaking, the rank 1 model has I say roughly speaking because there could be like some, different number of degrees of freedom depending if you use the SVD or not. But don't worry about this. Basically, the number of parameters here are number of movies plus number of users times R. So again, in our simple example, 100 users, 100 movies, 200, let's say that we use a rank of 3, which is what we will use, as we will see later on, for our real data. That's 600 parameters. So here we have to fit 600 parameters, estimate 600 numbers. So we only need to have seen, maybe 600 is basically pushing it a bit, but a couple of thousand entries from this matrix would suffice, and the total matrix has 10,000 entries, so that's not that crazy. Okay, so the cool thing is that now if we manage to estimate now I'm very committed to, so if we manage to estimate the entries in the low rank model from these observed entries, now we can combine this, this rank R matrix into an approximation of the whole matrix, which reveals the missing entries. So this is kind of cool, right? Like it's a very elegant way of completing the matrix. We're going to take a look at a detailed example in a moment, but we also need to emphasize that this is not magic. We're making a strong assumption, which is that the observed entries are enough to give us all the information that we need about the factors that matter to approximate ratings, and that we have enough of those observed entries to actually estimate those underlying factors. Okay, so here, Actually, I got things turned around. I thought I was going to tell you the limitations now, but no. Now I'm going to show you how to actually fit the rank 1 model. So let's take a look at how we fit a rank 1 model for this matrix. So here we only have 1, 2, 3, 4, 5, 6 observed entries. So we're not going to be able to fit a very complicated model. So we're going to be happy with rank 1. So what is a rank 1 model here? Remember, a rank 1 model is, we're going to say we have one column and one row. When we multiply together, we get a rank 1 matrix, and our assumption is that this rank 1 matrix approximates well the original matrix. In order to build it, we only need to estimate this column and this row. When we multiply out the column and the row, we see that essentially what we get, the same column but weighted by different values, here B1, here B2, and here B3, or conversely, the same row scaled by different values, A1, A2, A3. Okay, this is why it's a rank 1 model. But now we have to see if we can actually estimate these numbers from the observed entries. The first thing that we need to notice is that if we scale each of these guys by a constant and each of these guys by 1 over that constant, so for example alpha, then we get the same values. Okay, so we need to basically fix the scale of either A or B, and the way we do that is by just choosing that A1 is going to be equal to 1. Okay, that's what we do. And now I'm going to show you that you can actually solve this riddle, because what should B1 be equal to? Well, here we see that A1 times B1 is equal to 1, and we have fixed A1 to be equal to 1, so B1 is also equal to 1. What about B3? So B3 appears here, multiplied times A1, it's also equal to 1, so B3 also is equal to 1. What about A2? You might be tempted to say, oh, I have B1, so A2 B1, let's use this guy. That won't work. Think about why. Why? Because we have not observed this guy. Okay, so that doesn't work. We have to look for a place where we have all the information, and that is, for example, so I'm looking for A2. I know B3 here, right? This is equal to 3. I know that B3 is equal to 1, so this means that A2 is equal to 3. What about B2? B2, I can use this, for example, right? A2 times B2 is equal to 6. I know that A2 is equal to 3, so B2 has to be equal to 2. And finally, A3, I think I have a few different options, but let's go with I cannot use this guy because this is not observed, but I can use this guy. Okay, so A3 times B2 is equal to 4. I know that B2 is equal to 2, so A3 is equal to 2. Okay, so in this case, because I made up this example, the original matrix was actually rank 1, and we are able to reconstruct it exactly. How do we reconstruct it exactly? Where we have found these two factors, we just multiply them together, boom. We get the original matrix, in particular, the missing entries. Great, perfect. So now, and this is what I thought was before how to actually do it, is this magic? No, this is not magic. As we have seen while we were solving for this, we need to have observed certain entries in order to be able to estimate these factors. And if we were to carry out the same procedure for this matrix, we would see that when we get to this entry in the column vector corresponding to this rank 1 model, basically we cannot observe it because, we cannot solve for it because we haven't observed any entries within that row. So how are we going to retrieve that value? That's absolutely impossible. In the context of recommender systems, that's just like trying to estimate the rating for a movie that no one has seen. If no one has seen it, we don't have any information about the movie, we cannot estimate it. Or if a user has not seen any movies yet on Netflix or hasn't bought anything on Amazon, you can't do anything. Okay, you restrict yourself to a data set that is just observations of ratings So that makes a lot of sense. Another problem, so we need to observe enough information in every row and column to fit the low rank model and be able to perform the matrix completion. Another problem that we could run into is this one. So here in this true matrix, there's a pretty singular entry right in the middle, and we happen to not see it. We missed that one. Can we reconstruct it? Where if you build a rank 1 model here, you see that this factor, okay, this entry, is actually unrelated to the other entries. Why? Essentially because these guys are 0. Okay? And because of that, if we want to rebuild it, basically we cannot gain information from the observed entries. If you build a low rank model, you realize that you don't have enough information to know what the second entry in the column or the row is. This is because the information in this matrix is very singularly concentrated in one entry and you don't get to see that entry, so bye-bye. As an example, in the real world, imagine if someone, I don't know, tends to like Star Wars movie, but they really hate the first Star Wars movie because after that one, their girlfriend broke up with them. So if we don't know that and we have to guess what rating they would give to that first Star Wars movie, it's an impossible problem because their rating is completely unrelated to the ratings for other movies. Okay? So there's this assumption that we can only recover a low rank structure that is actually observed. Okay, so in practice, data is not going to be exactly low rank like in my cartoon example where the original matrix was indeed rank 1. So what we do is we try to approximate the data using a low rank matrix. And a typical metric to quantify how good the approximation is basically the square of the entry-wise errors. So we sum all of the entry-wise errors corresponding to observed entries. This tells you how well you're approximating the matrix. The problem is that if we want to minimize this cost function with respect to the factors in a low rank model, this is a non-convex cost function that is very difficult to optimize exactly. Interestingly, if you observe all the matrix, the singular value decomposition gives you an optimal solution to this problem, but that is no longer the case if you have missing entries. And this is, this slide shows you what I just said. If you truncate the SVD, as we discussed in the video of about low rank models, and this comes from the fact that PCA gives you optimal low dimensionality approximations, and the truncated SVD at the end of the day is equivalent to doing PCA on the columns or on the rows. Basically, you can get an optimal low rank approximation to a matrix if you observe all the entries of the matrix. If not, and here basically this is a norm that is the sum of the squared entries, and then we take a square root. Okay, that's the Frobenius norm. Basically, it's exactly the same as this, but with all observed entries. Okay, so the truncated SVD is optimal, but it's no longer optimal because you cannot just apply it, right? You cannot compute the SVD if you don't see all the entries when you have missing entries. So what can we do? Let's think about it a bit. What could we do here? Well, we could apply the truncated SVD kind of naively to a matrix where we have just imputed the missing entries with some reasonable values. Let's see what I mean by that. So first, we're going to center all the ratings. We're going to center them by removing the observed mean. Okay. So here, each value that you see here, okay, we have obtained it by taking the observed entry and subtracting the sample mean of all the observed entries. And now, what do we do for the entries that we do not observe? Well, we say, okay, since we have centered all the data by removing the sample mean rating, let's just put in a 0. because we don't know whether it should be higher than the mean or lower than the mean. Just put 0, which means basically, which implies that we're kind of saying, okay, in that entry, we're going to just put in the sample mean of all the ratings, and that's it. So now we can actually apply truncated SVD to this matrix and try to fit a low rank model that way. If we do that and we look at the singular values, we actually detect that the matrix can be well approximated as a rank 1 matrix. And you might remember that this is the case because this is the same matrix that we were using for the low rank model video, and there we saw that it could be well approximated as a rank 1 matrix, not exactly, but well approximated. Interestingly, and this is important, it's much less obvious than when you take the SVD of the full matrix. When you take the SVD of the full matrix, you can clearly see the rank 1 structure much more than when you take the SVD of the imputed matrix. Why? Because you see much less structure, right? These guys have been imputed to just be zeros. They should not. They each have like much more extreme values. But still, we can fit a rank 1 model to this imputed matrix. Basically, we compute the SVD and we just preserve. So we throw away all of these guys and we just preserve U1, which is the left singular value corresponding to the first singular vector, and the right singular value corresponding to the right singular vector corresponding to the largest singular value. And that gives us our rank model, a rank 1 model, and we're going to add back the mean of the observed ratings to get an approximation to the missing ratings. Okay, so we compute that out, and what we observe is that it's not so bad. Okay, like for example, here we get a pretty good estimate for the rating given by Mary to Superman 2, which perhaps is not that surprising because we have a lot of observed ratings for Mary and a lot of observed ratings for Superman 2. But Bob, where we observe less ratings, what do we observe? We see that his ratings are kind of lower than they should be for 5 and higher than they should be for 1 and 2. I should have said the real values are here in brackets. Why is that? Because we don't see that many ratings for Bob, and we had imputed the mean rating. Okay, so are we happy with this? We're not super happy because basically the ratings for Bob are being pushed towards the mean rating because obviously we're trying to approximate it, right? We're taking the SVD of the truncated SVD of a matrix where we have imputed that value. So it's kind of, we shouldn't blame the model too much that it's trying to fit it. But in that sense, this is not, this is not very satisfying. We're not completely happy. The bad news is that we're fitting the imputed values, which kind of makes sense because we're taking the truncated SVD of the matrix with the imputed values. But there is a silver lining here. There's some good news, okay? For some users, particularly Mary, but even also for Bob, you observe that the estimates are better than just imputing 2.94. So we have improved in a way. So what could you do? Well, you can repeat this, but now use these imputed values as opposed to the mean, okay? These imputed values to obtain a better matrix and then fit a rank 1 model to that matrix and iterate. And that's exactly what we're going to do. So we're going to alternate between imputing these improved estimates obtained with the rank 1 model and doing SVD truncation again to obtain a better rank 1 model. And this is a method called hard impute. It's a way of fitting low rank models to complete matrices, to perform matrix completion. There are other methods that also work very well, including gradient descent, alternating least squares, or convex relaxations based on the nuclear norm. Okay, so what happens when we alternate between imputing and low rank? So here I'm showing you the estimates for the missing entries. At the beginning, they are closer to to the mean rating, which is kind of there. And then after, not that many iterations, they converge to more extreme values. And here I'm going to show you that those extreme values are actually correct in this case. You can see particularly the estimates for Bob have become much better. Okay, the lower ones are closer to the lower values, the higher one is closer to the higher value. Okay, so our method worked. And now we're going to apply this method to real data. I'm going to use the Movie Lens dataset, which is available online. And the way I went about this is I extracted the 1,000 users and 100 movies with the most ratings. And like the total observed ratings are 30,000. So there's about 70,000 ratings missing. And I separated those observed entries into a validation set with 1,000 ratings, a test set with 1,000 ratings, and then the remaining approximately 28,000 ratings were used to fit the model. So what do? We're going to impute first the missing entries in a naive way. Here it works much better to impute the mean rating for a particular movie as opposed to imputing the mean rating over all movies or the mean rating for a particular user. That's just it works much better, so that's what we're going to do. And I had talked a little bit about this in the video on low rank models. The way you center the data, or in this case, what you use to impute the missing values at the beginning for each movie, might depend on the data set that you're using and the kind of structure that you want to exploit or you want to learn about. Here, the best thing to do is to impute using the mean rating for each movie, and I just found out empirically. So now we're going to alternate between truncating the SVD and then re-imputing with this improved estimate obtained from the truncating SVD to iteratively improve the imputed entries and the rank one, the low rank model. So here it's no longer going to be rank 1. We're going to truncate the SVD using a hyperparameter R that we need to decide. So how do we choose the rank of our low rank model? So, excuse me, I will tell you in a moment how we're going to do that, but how do you expect R to affect the training error? So in other words, what if we just monitor our training error, which means how well we're approximating the observed entries? I encourage you to stop the video and think about whether when you increase the rank of the low rank model, you're going to be able to approximate these entries better or worse. And the answer, I hope you stopped the video and thought a little bit about it, is that, well, eventually you're going to fit them perfectly, right? Because if you have a sufficiently high rank, you're going to be able to fit everything you see perfectly. However, if you have your validation set, you could check how well you're doing on the validation entries that are not used for your fitting procedure. And that there it's no longer going to be the case. And I should have asked you to think about this too. That you're going to necessarily do better and better as the rank increases, because at some point you're going to overfit the observed entries. And this is exactly what we observe with our data set. This is the root mean squared error for the observed entries, and not the observed entries, sorry, for the entries that are indeed observed, so in the training set, and also for these held out entries that we're using as validation. What we see is that the training error just decreases as we increase the rank, which makes a lot of sense because we have many more parameters. We're able to approximate the data set much better. However, eventually we overfit when we go beyond rank 3. So remember, actually, let me remind myself how many users and how many movies we have. Okay, now I'm in too deep. Okay, we have 1,000 users and 100 movies. So if the rank is 3, the number of parameters in the model is 1,000 plus 100 times 3. So that's basically around 33,000. Sorry, not 33,000. Well, my math is amazing, right? 3,300. We also have to add the mean rating for every movie. So this is plus 100. Because we're also using that as a parameter. So we have a model that has around 3,400 parameters, and we're using about 10 times more data to fit it. So that seems quite reasonable. Okay, it's quite reasonable that when we do this validation procedure, we find that rank 3 is a good balance between being complex enough to capture structure in the data and not being so complex that we overfit because we don't have enough data. Okay, so that makes a lot of sense. When we compare the root mean square error on our test, if we just look at the test mean squared error obtained by the mean rating of each movie, it's 0.97. We improve quite a bit to 0.89. And it's not so easy to improve this error. Okay, I encourage you, the data are online, like I'm going to publish the code, so you can try to improve. It's not so easy. And in fact, there was this whole Netflix challenge precisely to try to improve this. And by the way, these low rank models were a very important part of the winning strategies. Okay, so now I've shown you that you can use these low rank models to perform matrix completion with real data, and improve upon this simple baseline. Now we're going to analyze the model that we have fitted by looking at the components corresponding to the movies and the users. So remember, here we would have just 3 factors. So 3 components for the movies and 3 components for the users, and we're going to take a look. So our rank 3 model looks like this. We're taking the mean, this actually should be the mean of the movie in our model. So this actually should be M of movie. Okay, I apologize for that. This was for the mean of the whole imputed data. That would have been for a simple example, we're just averaging all the ratings, but here we're using the mean per movie, and we're adding to that this rank 3 model where we have these 3 factors. We have a coefficient for each movie associated to each of the 3 factors, and now we're going to look at them to see if they indeed kind of group similar movies. For the first one, the highest entries correspond to Dante's Peak, Volcano, and The Saint. I don't know if you have had the pleasure to watch these movies, but if you look at the Film Affinity ratings, essentially they're terrible movies. Okay? Whereas the lowest entries here are One Flew Over the Cuckoo's Nest, The Godfather, and Casablanca, all of which got a bunch of Oscars, so they were critically acclaimed. So it seems that the first factor distinguishes between bad movies and good movies. So we could interpret the corresponding coefficient for each user in terms of, do they like to watch trash movies or do they want to watch like critically acclaimed movies? Let's take a look at the second factor. These are the movies that had higher entries for the second factor: Volcano, Evita, Dante's Peak. So Dante's Peak is there again. Volcano also, right? Let me take a quick look. I forget, yeah, Volcano and Dante's Peak seem to be very polarizing. Again, very bad movies. Evita apparently is also a very bad movie. I haven't watched it. The lowest entries here are Titanic, Star Wars, and Raiders of the Lost Ark. So they're essentially movies that were extremely successful in terms of box office. Okay, so these are box office successes. These are bad movies that actually were not even box office successes. They were box office failures. Okay, so the second factor seems to capture commercial success. And finally, the third factor, let's take a look at the highest entries. The highest entries are Return of the Jedi, Star Wars, and Raiders of the Lost Ark. Again, highly commercial movies. Now, the lowest entries, however, are not like horrible movies like in the previous case. They're Leaving Las Vegas, Trainspotting, and A Clockwork Orange, which are all cult movies that are much edgier and darker than commercial movies like this. So this, in this case, this coefficient tells us basically whether the user prefers commercial like adventure movies or rather like edgier alternative movies. And again, I apologize for this. This should not be the mean of all the imputed ratings. It's the mean of each movie. Okay, if I post the slides, I will post them corrected. Okay, so what have we learned in this video? We have learned how to perform collaborative filtering using low-rank models, framing it as a matrix completion problem. We have learned how to fit these low-rank models to data, and we have applied them to a real data set to estimate movie ratings. And that's all I got. Thank you very much.